Hey students, let's talk a little bit about chapter 6. This is the last chapter of this section of the book on the center of the known universe. So, in the previous chapters 4 and 5, we've essentially talked about what we call a geocentric theory. Geocentric. Geo is Earth, centric is center. These are theories that have the Earth at the center of the universe and things going around them. Now, the geocentric theory is not without its problems. Okay? First of all, consider it wasn't that hard to figure out how big the Earth is. We'll do an assignment on that in class. But the basic idea is you measure a distance north to south on Earth. You go from one place to wherever you measured to the next place you measured. You measure how much the stars move. And, they move a certain number of degrees, which is proportional to the full 360 degrees of a circle around a round Earth. We have reason to believe the Earth is round, as we discussed in previous chapters. And then you work out that proportionality to the amount of miles you moved, and you calculate the size of the overall Earth. Turns out the biggest difficulty with this is actually surveying how far you went on the ground. So you work out, and you find out the Earth is big, 25,000 miles around. And then you figure, okay, the stars are up beyond the Earth, so as they go around the Earth, they're going in a very large circle once every 24 hours. And it basically they didn't know exactly how far away the stars were, but they figured, they were able to do some basic calculations that the stars had to be darned far away, and therefore moving in a darn big circle around Earth, and therefore moving incredibly fast to go through that whole circle once every 24 hours. And that seemed really, really hard to believe, that these stars would be just moving at these incredible speeds. The other strange thing about the geocentric theory, that is specifically about the epicycle theory, is that the wandering stars, when they went through their retrograde motion, we talked in the last chapter, as they go through retrograde motion, they get brighter. The middle point of that retrograde motion and the point of maximum brightness of the wandering star was synced to the motion of the sun. And there wasn't any real reason why that ought to happen. Okay, remember that we described the epicyclic motion as being like a scrambler ride. Okay, it was determined by one circle turning and moving on another circle. Right? The sun's not part of the picture. So why is it that for some reason the point where the wandering star always got closest to Earth and went through its backwards retrograde, the retrograde motion, why did that always occur when the sun was in a particular position, and specifically when the sun was opposite the Earth from the wandering star, so that you had the Earth here, the wandering star over here, and the sun over here. Okay, these were always occurred in a line when the retrograde motion and the maximum brightness was going on. There wasn't any real explanation for that this should be linked to the sun. It just happened, and nobody really knew exactly why. The other thing was that the sun was big. Okay, it's not too hard to do some basic calculations. You can look in the appendix of the book, I think Appendix A, if you want to see how this calculation was done. We will do a version of it in one of our miscellaneous assignments in class. But it's not too hard to go and calculate that, the sun has to be a lot bigger than the moon, and turns out even a lot bigger than Earth. So, does it seem odd that a big sun goes around a little Earth? Maybe that seemed kind of odd to people. This is all 2,500 years ago, and the guy who did the calculation on the size of the sun was a Greek named Aristarchus. Okay, another one of these Greek thinkers and scientists. So Aristarchus, perhaps because of these problems, we don't really know why, he proposed an alternative theory to explain everything we see in the heavens. He said, no, the Earth is not at the center of the universe. The sun does not go around the Earth. He said the Earth goes around the sun. All right, so this is called a sun-centric. Helios is the sun. Okay, it's at the center. So heliocentric theory. The Earth goes around the sun. As the Earth goes around the sun, our perspective on the sun changes, and that's what causes the sun to appear to move through the stars on that yearly cycle. And then the Earth rotates about its own axis once every 24 hours. and that's what causes the rising and setting of the sun. And then the moon orbits around the Earth once every 30 days, and that causes the lunar cycle. All right, this is the heliocentric theory. We don't know that many details because Aristarchus' writing on the heliocentric theory is lost. The reason we know that he did this is because there are writings of other people talking about how Aristarchus came up with this theory. But we don't have Aristarchus' theory and his thought processes on it themselves. All right, well, there's problems with this theory, okay? Heliocentric theory, problems. Well, first, okay, the heliocentric theory gets rid of the fast-moving stars, but it replaces that problem with the problem of the fast-moving us. Okay, so if we are on the Earth is 25,000 miles around, then the people who are down on the equator going around the Earth once every day move 25,000 miles in 24 hours, and that's over 1,000 miles per hour. No, that's not as great as the speeds of the stars in geocentric theory, but nonetheless, it's awful fast to be going over 1,000 miles an hour and to say, I can't detect that. Even up here in Kentucky, we're going over 800 miles an hour if Aristarchus is right. So that's one problem. I mean, do we really think that we're going at those kinds of speeds and we can't detect the motion? Second problem with the heliocentric theory. Okay, what powers the motion of the Earth? In the geocentric theory, so well, what powers the motion of the stars? The prime mover. Okay, plus the stars, the sun, they're all made out of that fifth element stuff, none of which exists down here. So that fifth element must, we can explain that away. We can say the fifth element is light and strong and, it's not hard to make it go, or it naturally moves on its own, just like a rock naturally falls to the center of the Earth. Fifth element naturally moves in circles. It's easy to explain away the motion of something that we don't have a sample of it here on Earth. Okay, we can invent theories to make that work. It's another thing to come up with an explanation for how do you make a ball of rock, the Earth, 25,000 miles around, move. Because we know what rock is. We know that even a wagon load of rock is very hard to make move. And therefore a ball of rock 25,000 miles in circumference is going to be incredibly hard to make move. And what is going to power this whole thing? After all, you don't have a prime mover in the heliocentric system, because the prime mover in the geocentric system was out beyond the stars and powered the whole thing. There's no prime mover. There's no way to make this Earth go. What is it? You're postulating the idea that the Earth is turning, going quite a speed, just turning, and then it's going around the sun, and that speed is even more incredible. What makes it all move? Okay, no good answer. All right. The third problem was the problem of parallax, okay, which is, I'm looking at this camera here talking. If I move over here, or I move over here, if I move my head around, my perspective on that camera changes. As I move closer to it, it's a little bit larger, further, a little bit smaller. I'm looking at it from one angle, I'm looking at it from the other angle. The stuff around it, they all change their position. When you look at something nearby and you move your head around, all the positions and angles all change. Okay. Well, the argument was, well, look, if the Earth is going around the sun, then as we view the stars, their positions and angles should also all change. This is what's called annual parallax. Annual, because it was the motion of the Earth around the sun every year. It was called annual motion. And then parallax is this changing in positions and angles. If the Earth is moving, shouldn't we see some annual parallax up there in the stars? We don't. So that would seem to suggest the Earth is not moving. Now, the heliocentrists could come up with some answers to this. For example, Aristarchus had an answer for the parallax, and you can imagine another one for the problem of our speed. But Aristarchus said, well, look, what it is, the reason we don't see any parallax in the stars is because they're really unbelievably far away. They're so far away that our little motion in a circle around the sun is nothing compared to the distance to the stars. So, while it might be true that camera over there, its position, its angles, so on and so forth, changes as I move my head around. If I look off at some distant tree that's on a hill a couple miles away, and I do that with my head, it doesn't affect anything. Why? Because my motion is too small relative to the distance of that tree for it to make any difference. And so Aristarchus said the stars are just really, really far away. That's why we don't see any parallax in them. The speed, you could kind of say, well, if everything's moving together, then we wouldn't notice it. So if everything so I could say, well, maybe I'm going 800 miles an hour right now, but the books are going 800 miles an hour, the wall's going 800, we're all going 800 miles an hour together, and so we wouldn't notice it. Those arguments could work, but someone who was a geocentrist would say, really, do we need to do all that? Isn't it simply more reasonable to suppose that we're at rest? You still haven't answered the power problem. What makes the Earth go around the sun and spin? So perhaps it would be just more logical to say the Earth is at rest and everything's going around us. And yes, the sun is larger than the Earth, but it's made out of the fifth element, so it could just be like this big glowing soap bubble in the sky. It has no weight at all, but it's incredibly strong due to the fact it's made out of the fifth element. So the heliocentric theory didn't exactly catch on because of the various problems with it. It seemed like, not that the geocentric theory didn't have its own problems, the heliocentric theory, apparently its problems were a little bit harder for people to accept, and so the geocentric theory, especially that of Ptolemy with the epicycles, dominated for a very, very, very long time, from Aristotle, who's like 2,500 years ago, all the way up to Copernicus. So almost 2,000 years. And not quite. Aristotle's not quite 2,500 years ago. Hope this helps with Chapter 6. Remember, these talks are no substitute for reading the book, and they're not meant to be. By no means am I covering everything in those chapters. Thanks.